In 2025, a duty operator at the LIGO gravitational-wave detector suddenly jumped out of their chair, because the screen showed that a star had exploded twice. The first explosion had barely ended, when the second one followed immediately after, with an interval of less than a few seconds. It was like watching someone die with your own eyes, and then seeing them suddenly explode again inside the coffin. Even more absurd, within the explosion's debris they discovered a neutron star that was lighter than the sun, but according to the laws of physics, it simply should not exist. It was so light that it should have been an ordinary star, yet so dense that it had to be a neutron star. It was like discovering a piece of ice that is both liquid and solid at the same time. That very night, 17 observatories around the world simultaneously pointed their instruments at this region of the sky, because everyone realized that the universe had just shown us a way of dying we had never seen before. So here's the question: if stars can really die twice, how much of what we think we know about the universe is actually wrong? To understand just how insane this discovery is, we first need to clarify how many ways stars can die. Before 2025, astronomers believed there were only three mainstream types of stellar explosions in the universe: novae, supernovae, and kilonovae. Each of them followed a fixed script. A nova is a small-scale explosion caused when a white dwarf siphons material from a companion star. A supernova is the core collapse that marks the end of a massive star's life. And a kilonova is the explosion produced when two neutron stars collide. These three types of explosions are like three different methods of execution: the guillotine, the electric chair, and the gas chamber. Each has its own procedure, and they never get mixed together. But the observation in 2025 completely overturned this classification system. In the first few days, all signs pointed to a standard kilonova. It faded rapidly and emitted intense red light. Spectral analysis showed it was rich in heavy elements like gold and platinum, and the gravitational wave signal confirmed the merger of two compact objects. Astronomers breathed a sigh of relief, thinking this was just a replay of the historic 2017 discovery. Another paper to write. Job done. Then, on the fifth day, things suddenly became strange. This kilonova, which should have continued to fade, started to brighten again, and kept getting brighter. Its color shifted from red to blue, and large amounts of hydrogen and helium suddenly appeared in its spectrum. It was like performing an autopsy, only for the corpse to suddenly sit up and say, "I can still be saved." Everyone was stunned, because hydrogen has no place in a kilonova spectrum. That's a signature of a supernova. Worse still, the hydrogen gas was moving at speeds of up to 17,000 kilometers per second. Velocities like that only appear during core collapse supernova explosions. So what did this mean? It meant that what we were observing might not be a single explosion at all, but two completely different explosions, occurring in almost the same place at almost the same time. It was like finding both gunshot wounds and stab wounds at a crime scene, and discovering that both were inflicted in the same second. According to traditional theory, this should be impossible. Supernovae and kilonovae have entirely different formation mechanisms. One comes from the core collapse of a single star, the other from the collision of two neutron stars. How could they possibly occur in the same place? But an even bigger problem was still to come. When scientists carefully analyzed the gravitational wave data, they uncovered an even more devastating contradiction. The signal indicated that the merger involved at least one neutron star, whose mass was actually lighter than the sun. That may not sound like a big deal, but in astrophysics, it is nothing short of absurd. According to all existing theories and simulations, a neutron star must have a mass between about 1.2 and 3 times the mass of the sun. Any object below 1.2 solar masses should not be able to collapse into a neutron star at all. It should become a white dwarf instead. It's like discovering an NBA player who is only 4 feet tall. By every rule of human physiology, someone that short should never make it into the NBA. And yet there they are, playing on the court. Scientists were plunged into deep confusion. If this subsolar mass neutron star truly exists, then the stellar evolution theories we've built over the past decades may need to be torn down and rebuilt from scratch. To explain this unprecedented phenomenon, scientists proposed a hypothesis so bold it borders on madness. They call it the superkilonova. The scenario described by this model sounds like pure science fiction. Imagine a massive star rotating at an almost unimaginable speed. When this star reaches the end of its life and begins to collapse, its rotation is so extreme that its core does not collapse cleanly into a neutron star or a black hole, as in a normal supernova. Instead, the core splits apart during the collapse. The process may unfold like this. The rapidly rotating core forms a massive accretion disk, which, under extreme conditions, fragments into multiple pieces. At least 2 of these fragments collapse into low-mass neutron stars, and these newborn neutron stars are absurdly close to each other. They are practically born touching. Their orbital period may be only a few milliseconds. The result is that the moment these neutron stars are born, they begin spiraling toward each other at a furious pace, and collide within just a few seconds. So what we are actually seeing is a superposition of two explosions. On the outside, there is a normal supernova explosion. The star's outer layers are blasted outward by the shockwave from core collapse, expanding into space. And inside this expanding fireball, two miniature neutron stars are performing their final dance of death. Their merger generates gravitational waves, and releases the red light and heavy elements characteristic of a kilonova. At first, the red light we observed came from the kilonova shining through the supernova's outer shell, but as the supernova envelope continued to expand and brighten, its blue light gradually overwhelmed the red glow of the internal kilonova. That is why we observed the bizarre transition from red to blue. If this theory holds up, it would completely rewrite the textbooks on stellar evolution, because it would mean that under extreme conditions, a single star can give birth to two new neutron stars at the moment of its death, and those two neutron stars will immediately destroy each other. This kind of birth and death scenario is something we had never imagined before. More importantly, it offers a possible formation pathway for neutron stars with anomalous masses. But scientists remain cautious. They emphasize that this explanation is still far from conclusive, because many aspects of the event remain unexplained. For example, if two neutron stars really did merge, we should have detected strong X-ray and radio emissions. But in this observation, no such signals were found at all. It's like watching two cars crash into each other, without hearing any sound of impact. Clearly, something is off. There is an even more troubling issue. Although the gravitational wave signal and the optical observations occurred close together in time, calculations show there is still a 2% to 4% chance that they were not the same event at all. In other words, the gravitational waves may have come from one neutron star merger, while the optical explosion came from a completely different star. They just happened to occur at roughly the same time and in roughly the same direction. The probability of such a coincidence is low, but it cannot be entirely ruled out. It's like hearing a thunderclap and seeing a flash of lightning at the same time. You naturally assume they came from the same lightning strike, but it's also possible that two different lightning strikes occurred in the same second. If that's the case, then this observation isn't a superkilonova at all, but a massive cosmic prank played on us by the universe. To determine which scenario is correct, scientists now urgently need to find more events like this one. They hope that in the coming years, gravitational wave detectors will capture similar signals again, and next time, they will deploy every top-tier instrument available, including the James Webb Space Telescope. Webb's infrared capabilities could allow us to see through the supernova's outer shell, and directly analyze the composition of the material inside. If heavy elements produced by a kilonova are truly found mixed within supernova ejecta, then the superkilonova theory would be confirmed. The significance of this discovery goes far beyond identifying a new type of cosmic explosion. It reveals a much deeper truth. The universe's creativity far exceeds our imagination. We are always trying to categorize cosmic phenomena, to organize them neatly into labeled boxes, but the universe refuses to follow our scripts. It creates things we believe should not exist, then places them right in front of us and says, "Go ahead. Explain this." Take precious metals like gold and platinum. We once believed they could only form in kilonovae, but if superkilonovae really exist, then the universe has another kind of alchemy. The gold ring on your finger may not have come from the gentle collision of two neutron stars, but from the violent fragmentation and self-devouring death of a single star. That story is far more brutal, and far more dramatic. Right now, observatories around the world are on 24-hour alert, waiting for the next similar event, because if this theory is confirmed, we will have to admit that our understanding of the universe may not even reach 1%. Those physical laws we believe we have mastered may be nothing more than the most ordinary, most boring rules in a much larger system. And the truly spectacular parts, the extreme conditions capable of creating miracles, we may only be brushing against the surface for the very first time. So the next time you look up at the night sky, remember this story. Behind those seemingly calm points of starlight, there may be scenes unfolding that are wilder than any science fiction film. A star may be spinning tens of thousands of times per second. Its core may be splitting into two fragments, and those fragments may devour each other in the very next moment, creating a cosmic fireworks display the universe has never seen before. And all of this is happening for one simple reason: to tell us a fundamental truth. In this universe, nothing is truly impossible.